Hello everyone, I'm Paul and today we're solving problem 1931, painting a grid with 3 different colors. This is a hard problem, so here we will start small and expand the logic with each step. So keep watching for the intuition, approach and efficient solution. We're given two integers m and n representing the size of a grid, and each cell in the grid is initially white. Now our job is to paint each cell with red, green or blue, and all cells must be painted. And we need to return the ways to color the grid. But here we have a restriction. No two adjacent cells can have the same color. And given that the answer can be large, we need to return it modulo 10 to the power of 9 plus 7. Now let's say we have this grid. This is a 1 times 1 grid, and we can paint this red, we can paint this green, or we can paint this blue. This means we can paint this in 3 different ways, so the result for this grid is 3. Now let's say we have this grid. We can paint this cell with red, green or blue, and we can paint this cell with red, green or blue. So we can have these combinations. We can have red and red, red and green, red and blue, green and green, green and red, green and blue, blue and blue, blue and red, and blue and green. So these are 9 possible combinations. This means that in a grid of 2 cells, we can have 3 times 3 combinations. And similarly, if we have a grid of 3 cells, for example, we have 3 times 3 times 3 combinations. So now I think you see the pattern here. We have 3 to the power of the row length combinations. And given that m is smaller or equal to 5, we will take m as the size for every row. So we have 3 to the power of m combinations for every row. Now maybe you are thinking about taking n as the size of the row, but that's not convenient. You will see why in a few minutes. Now that we know that these are all the possible combinations for every row, we will do like a simulation for each of these combinations. And we will store every possible combination in something like a bit mask. But instead of using bits, which are zeros and ones, we are using base 3 numbers. We are using something, I guess it's called treats. We are using zeros, ones and twos. And by doing this, I think it's called treat masking. We can store every possible combination, and then we can filter every combination we don't need. For example, here we have 2 adjacent reds, so this is not valid. This is also not valid. This is also not valid. Now, in case you don't know how to do bit masking, let's see how this works. Let's say we want to find a base 2 number. This is the same as a binary number or a number represented in bits. Every bit in position 0 has a weight of 2 to the power of 0. This means 1. Every bit in position 1 has a power of 2 to the power of 1. This is 2, and so on. Now, let's say we are trying to represent the number 5. Well, to reach 5, we can take 1 4 and 1 1, and 4 plus 1 is 5. So this in binary is 1 0 1. Okay, so this is for numbers in base 2. Now we can also represent a 5 in base 3, and the logic is the same. For the position 0, we are taking 3 to the power of 0. This is 1. For position 1, we are taking 3 to the power of 1. This is 3. For position 2, we are taking 3 to the power of 2. This is 9. And so on. We could continue with this. Okay, so if we are trying to represent a 5, we could take 1 3 and 2 1s, and 3 plus 1 is 5. So 5 in base 3 is 12. Now let's say we're trying to represent 50 in base 3. We could take 127 plus 2 9s, so this is 18, plus 1 3 plus 2 1s, and this is 50. So here we have 127, 2 9s, 1 3, and 2 1s. So 50 in base 3 is 1 2 1 2. Okay, now let's go back to the problem. We know that for each row we can have up to 3 to the power of m possible combinations. So we will store each one of these combinations in a map, and we will store this in the form of the number of the mask, and this will have as a value an array with the current combination. So for example, we could have the key of 0, this will be equal to some array, the key with 1, this will have another combination, and so on until we have the key of 50, for example, and this will be an array with 2 1 2 1. So we are building every unique combination from the current key. So for example, remember that 50 in base 3 is 1 2 1 2. And the way we are doing this is we take the last element, we put this into an array, we remove this from the current number in base 3. Now we have 121 only. We repeat the same process with the 1, we do the same with the 2, we do the same with the 1. Okay, so for example, let's suppose m is 4. If m was 4, here we will have in our map for the key 50 an array with 2 1 2 1. Okay, now with this approach we will get every possible combination, but we need to filter this map because remember that adjacent colors need to be different. So for example, if we have an array with 0 0 0 0, we can't use this. Okay, so our final map will include only valid rows. Now we have a map with all the possible valid rows. So let's say this includes a key of 50 with this valid array, which is 2 1 2 1. Now we can iterate this with this again in nested for loop and check which are the valid adjacent rows. So this will be another map with the form of mask 1 has an adjacent row of mask 2. So for example, let's say that here we have another key with the combination 1 2 1 2. This could be valid adjacent rows because these values are different, these are different, and so on. So here in this new map we could store 50 with a value of this mask. Okay, and now finally, once we have every valid adjacent row, we can do a DP to expand this same logic to every other row up to n, because remember we are using m for columns and n for rows. And I forgot to tell you why we are not using n for rows, because remember we have 3 to the power of m possible masks. But remember that m is 5 and n is 1000. So if this was n, we would have 3 to the power of 1000 masks. This is a very huge number. So to make this possible, we need to take m as columns. So up to this point, we have a map with valid rows, another map with valid adjacent rows, and now we are building a DP to get the final answer. Now let's say n equals 3 and we are starting from any valid row, let's say this one. And from this we are taking the rows that are adjacent and are also valid. Let's say, for the sake of this example, that the only adjacent rows from this one are these. Now remember, this is for the level where n equals 1. This is for the level where n equals 2. So in this side we could build this grid, and in this side we can build this valid grid. And let's say we have one more level here. So this is where n equals 3, and up to this point we can build these grids. We can build these two and these two. So here we have one valid adjacent row. Here we have another valid adjacent row. Here is another one, and here is another one. This means that up to this point we can build two valid grids, and up to this point we can build other two valid grids. And finally, this means that with this fixed row we can build 2 plus 2, 4 valid grids. So we add 4 to our result, and we repeat this same process with every valid row. So we are taking a valid row as a fixed row, and from there we are doing a DP for every adjacent valid row, and then we are just adding every possible combination. And finally, after all of this, we return the result. So this is it for the approach, and now let's go with the code, and hopefully you will get the idea. First, mod equals 10 to the power of 9 plus 7. Then valid will be a dictionary, and then we are creating our treat mask. So for every key in range from 0 to 3 to the power of m, we will have an empty row. We will say the current mask is our current key, and for I in range m, row dot append mask modded by 3, and then we subtract from mask the last treat. So mask divided equal 3. Okay, and now we need to filter the combinations that are not valid. So if not any, we can do this in Python. Row at j equals row at j minus 1 for j in range from 1 up to m. So if the combination is valid, we add to valid with the current key the current combination row. Now we are building the map for valid adjacent rows. This is like an adjacency list of height 1. Okay, so adjacent equals default dictionary. This will have a default value of an empty array. we do this like this, and for every mask, we will call this mask 1, row 1 in valid.items, and we iterate this again. So for mask 2, row 2 in valid items, if not any, we need to filter again here. If the adjacent colors for every column are different, in this case we can add the masks to the map. So if not any, row 1 at I equals row 2 at I for I in range M. So if this is okay, adjacent at mask 1 dot append mask 2. Okay, because we can have more than one valid mask for every row. That's why here we put an array here as a default value to store more than one possible combination. And now we have all the information to expand this logic to every other row. We can do a recursive DP or an iterative DP. In this case, we'll use a recursive DP. So DP, this will take an index and a mask. And first, if I equals n, we return 1. We will start with a count of 0, and now for every adjacent valid row in adjacent at mask count equals count plus dp with I plus 1, the current row, and we need to mod this. And finally we return the final count, and here we'll say result equals 0. Finally we will return this result, and here in between for every mask in valid, result equals result plus dp with 1 and the current mask, and this is modded by mod again. So remember, we are taking every valid mask as the fixed first row for every possible Greek combination, and from here we are doing a DP to expand the logic to every other row, and then we move to another valid row and so on, and each time we are adding to our result this count. Okay, and finally we return the result. Now about time complexity, in this part we have big O of 3 to the power of m times m, and in this part we have 3 to the power of m times n. So overall time complexity is big O of 3 to the power of 2m times n, and space complexity will be big O of 3 to the power of m times m, which is what we need here, and this is overall big O of 3 to the power of 2m. So this is it for the code, and now let's submit this and see if it works. Here I was missing a very important part, and it's that we need to cache every state for every I and every mask. So now this should work. Let's try again. And as you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.